So we'll now move on to 12 of the CFA curriculum that deals with multiple regression and the concepts therein. So we'll start with an introduction and the formulation of multiple regression, revise the concept of p-value from the level 1, understand the F statistic test that we missed at simple linear regression, saying that we'll cover it during multiple regression. The coefficient of determination will come again, and we'll also look at a concept called adjusted R-square, using the ANOVA table in a lot more detail now, the concept of dummy variables. Many times in real world applications, we see that our dependent variable, let's say stock returns, is not just dependent on any one factor. The stock returns for a particular sector or a particular industry may have seemed to be related with the valuation, with the GDP growth, with the general market return, and even some other factors. If the relationship of the sort as described, then the simple linear regression that we studied in the previous review will not be able to entirely capture the relationship between the stock returns and the independent variables. So in multiple regression, we call it multiple because there is more than one independent variable. The dependent variable is still one, but there are many factors going into the dependent variable calculation. Now, we will still have an intercept term that basically gives us the value of the dependent variable when all the independent variables are equal to 0. So if x1, x2, xk are all 0, then the value of the dependent variable is equal to the intercept term. That is the same interpretation as from linear regression. The calculation of the slope coefficient now, that is, what is the dependence of stock returns to the P/E ratio, or what is the dependence to the GDP, or what is the dependence of the stock returns to the returns on the market, will have a slightly different interpretation now. The slope coefficients in multiple regression are referred to as partial slope coefficients. The slope coefficient B1 represents that how much would the value of y change for a 1 unit change in x1, keeping all other variables constant. So if I keep GDP growth constant, the return on market constant, and just increase or decrease the P/E by 1 unit, what would be the change in the dependent variable or the stock returns? If I change GDP, keeping all other constant, what would be the change in the stock returns is what the interpretation of B2 would be. So each of these slope coefficients represents the change in the dependent variable for a 1 unit change in the independent variable corresponding to that coefficient, keeping all other independent variables constant. So the dependent variable is a function of many independent variables. The yi is the ith observation of the dependent variable. Xj is the independent variable, x1, x2, x3, so on and so forth. B0 is the intercept term. B1, B2 are the slope coefficients for each of the independent variable. How the regression is performed is conceptually similar to what we did in simple linear regression. That is, we will calculate historical values of y given the values of x. We will see the stock returns for the last 30 quarters, for example, and the last 30 quarters, let's assume the stock gave a 2%, minus 5%, sometimes a 10%, 2%, 7%, so on and so forth return. During each of these 30 quarters, I would correspondingly measure the P/E multiple of the stock. Let's say it was 10, 12, 11, 9, 10 in the range. I will also measure the GDP growth for each of the quarters, and I will also measure the return on the stock market. So this will give me my historical data of the stock return with the return or with the variation on the independent variable. Question still remains, I need to calculate these coefficients b1, b2, b3, and I need to estimate the intercept term b0. Let's assume that I'm able to estimate these coefficients. The regression equation then would be written as y hat is equal to b0 hat plus b1 hat into x1 plus b2 hat into x2, so on and so forth, bk hat into xk. Please remember, we put a hat on top of a statistical variable when the variable is an estimated value and not an actual value. In the previous example, we were trying to place these actual returns as a function of the actual independent variables at that time. When we derive a regression equation based on those historical values and now use the regression equation for future prediction, that is, in the future, I am given a P by E value and I'm given a GDP growth number and I'm given a market return number, and I need to predict the stock returns or the expected stock returns. That is how I use my regression equation, or this is what I'm basically doing the regression for, so that I'm able to predict future returns on the stock. When I'm using it for the prediction and I'm using the estimated values of B1 and B2, then I put a hat on top of the statistical variables. The question remains, how is B0, B1, B2 derived? Please note once again, the derivation is not given in your curriculum. However, for better understanding, we will understand how it is done. The method is the same as that used in linear regression, wherein we were given a scatter plot and we tried to find the best fit line. We defined best fit as the line that minimizes the sum of squared errors. Please note, in the case of multiple regression, it will be relatively tougher to imagine the equation as a straight line on a plane, since there's not just two variables. There is 3, 4, probably even 10 variables. So the graph will not even be three-dimensional. The dimensions cannot be represented on a plane. But please understand, the concept still remains exactly the same. We will assume the predicted value to be b0 plus b1 into x1, so on and so forth. And for at least the historical values, we also know the actual values of the dependent variables for the last 30 quarters. For the last 30 quarters, we can calculate the error term as the actual value of y minus the predicted value of y. And predicted value of y is nothing but the regression equation. Please note, at the moment, all the coefficients are unknown. For the last 30 values, however, for the 30 quarters of data that I had in the previous example, can I compute 30 such expressions? Given x1, I know the y. Given the values of x again for the second period, I know the actual value of y. If I square each of these expressions, that will be called the squared error. And once again, the regression equation is the equation that minimizes the sum of squared errors. So once again, I will sum up all the squared errors for the 30 observations and minimize them. To minimize now, I will take the derivative of this expression of the entire sum of 30 errors, squared errors, with respect to b0 first and equate it to 0. Then I'll take the derivative with respect to b1 and again equate it to 0. I will be able to give k plus 1 such derivatives. If I have k independent variables, then there will be k plus 1 coefficients, one intercept coefficient. And each of those derivatives I can equate to 0, and I will get k plus 1 equations that can be solved to derive each of these coefficients. We did the same exercise during simple regression, that is during the previous session, and wherein the coefficient calculation came out to be the covariance of the dependent variable with the independent variable upon the variance of the independent variable. Please note that in multiple regression, the coefficient calculation is not that simple, and the derivation or the solution of this equation does not come out to be such a simple calculation. That is only for linear regression. What the exact value will be is too complicated and is beyond the scope of discussion, but just know conceptually how we derive the multiple regression equation. It is the same ordinary least squares method. That is, we minimize the sum of squared errors. So let's do an example. 20 years of block-up's annual sales were regressed against two independent variables. IP is the level of industrial production, and delta I is the changes in expected 10-year inflation expressed in decimals. The regression equation comes out to be that block-up sales are 8 units plus 0.005 times the level of industrial production minus 22.5 times the change in expected inflation. So how would we have derived these coefficients? We know it is the same last 20 years. I know the actual sales, I know the actual industrial production, and I know the actual change in inflation. And I would apply the ordinary least squares method again to find out that to what extent are the sales linked to industrial production and to what extent are they linked to the change in inflation. The coefficient 0.005 indicates that if industrial production goes up by 1 unit, block-up sales will go up by 0.005 units. Delta I, or the coefficient 22.5, indicates that if expected inflation changes by 1 unit, the sales will go down by 22.5 units. If expected inflation goes up by 0.01 units, the sales will go down by 0.225 units. Similarly, we are also given the standard errors of each of the coefficients. Always remember that these coefficients, whether in simple linear regression or in multiple regression, are estimates. They are estimated from this 20-year of block-up sales data. Had I used a different sample, had I used 21 years of data, had I used some other 20 years, not these exact 20 years, these coefficients may have been different. The coefficients are estimates. The coefficients will have a standard deviation. The standard deviation of these coefficients is referred to as standard error, a very important input that will go in the calculation of the statistical significance of each of these coefficients. The calculation of the standard errors, however, is again beyond the scope of your curriculum. The standard errors for you, or for the most part, will be given. However, you need to know how to apply these standard errors, as we will see in the coming slides. Once again, for the sake of repetition, let's interpret the multiple regression results. So 0.005 indicates that if delta I is constant and just the industrial production goes up by 1 unit, block-up sales will go up by 0.005 units. The minus 22.5, that is the coefficient of delta I, indicates that if the industrial production remains constant and just the inflation increases by 0.01 units, then the sales will fall by 0.225 units. These are called partial slope coefficients. The intercept term represents that when both IP is also 0 and change in expected inflation is also 0, the sales are expected to be 8 units. Just like we did a hypothesis test of the individual coefficients in linear regression, we can perform the hypothesis test for each of the coefficients in multiple regression. The null hypothesis in all statistical significance tests for coefficients will be that the coefficient equals 0. The objective of this analysis is to reject this null so that we imply the alternative that the coefficient is not equal to 0, and we can use the results of our regression. The test statistic for this test is a t-statistic, that is, it follows the t-distribution, and the test statistic is calculated as the estimated value minus the hypothesized value upon the standard error. If the t-statistic is greater than the critical value or less than minus of the critical value, then we will reject the null. Otherwise, we will fail to reject the null and we will conclude that the coefficient is not significantly different from 0. So if we fail to reject the null, then we cannot use the results of the regression, as we are concluding that it is not significantly different from 0. Please note, the t-test in regression has n minus k minus 1 degrees of freedom. In linear regression, recall this was n minus 2 because k was 1. K is the number of independent variables in the analysis. The confidence intervals for the regression coefficient are also calculated in the same manner. So whatever is the estimated coefficient plus minus the standard error into the critical value will give us the confidence interval of the regression coefficient, the same as in linear regression. We will now revise an interesting concept called p-value from level 1. So please recall that p-value is defined as the smallest level of significance for which the null hypothesis can be rejected. So to do an example, let's assume that we are performing a z-test. Z-test assumes the normal distribution. In the analysis, the test statistic came out to be 1.97. If the test statistic came out to be 1.97 and it is a two-tailed test, then please tell me that at 2% level of significance, will we be able to reject the null or not? Now please recall, in a two-tailed test, if the level of significance is 2%, that means the rejection region will have 1% on the right hand side and it will have 1% on the left hand side. The critical value for a 2% level of significance hence will be given as 2.33 units. Such that if the calculated test statistic is greater than 2.33 or less than minus 2.33, the null hypothesis will be rejected. In our example, the calculated test statistic is 1.97. So is 1.97 more extreme than 2.33? It is not. So at a 2% of level of significance, we do not reject the. Let's assume we increase the level of significance to 4%. For a 4% level of significance, we'll be leaving 2% on the right and 2% on the left. You can verify from the Z table that if you're leaving 2% on this side, then again the value would be higher than 1.97 or you will be unable to reject the null. For a 5% level of significance, however, we leave 2.5% on the right and 2.5% on the left. And please recall, and you need to remember these values for the Z table. So remember the T table, you don't have to remember the values. But the Z table, standard 95, 99, 97.5% values need to be memorized by everybody. So at a 5% level of significance on a two-tailed test, that will leave 2.5% on the right hand side. The critical value will come out to be 1.96. So with 1.96 as the critical value and the calculated statistic as 1.97, will we now be able to reject the null? Yes, because it is more extreme than the critical value. So remember, the p-value is the smallest level of significance for which the null can be rejected. For 2%, it could not have been rejected. For 4%, it could not have been rejected. 5% is the minimum at which I can reject the null. Similarly, at 6%, 7%, 10%, I will be able to reject because the critical values will be further narrower. So if 1.97 was extreme, or if 1.96 rather was extreme, all lower values will also be able to reject or make me reject the null. In a question, if the p-value is given to be 5%, implies that in this regression, the calculated test statistic is something like 1.97. That is, the minimum level of significance required to reject the null is 5%. If the p-value is given to be 10%, that means the minimum level of significance required to reject the null is 10%. The p-value essentially is another way of conducting the hypothesis test. So instead of comparing the critical values, I can simply compare the p-value with the level of significance given in the question. If the p-value is less than the level of significance given in the question, then the null hypothesis can be rejected, because the minimum value I need to reject the null is the p-value. If our actual level of significance is higher than the p-value, then the null can be rejected. If the p-value is greater than the significance level, so in this case, the p-value was 5%, but our actual level of significance initially was 2%. So could we reject the null? No. If the actual level of significance is lesser than the p-value, the p-value is greater than the level of significance, then we do not reject the null, or we fail to reject the null hypothesis. We'll do one example and understand this better. So we are given the intercepts and the coefficients. We are also given the standard errors. Please note the t statistic is simply the coefficient divided by the standard error. So you can verify that the t statistic here is matching. Up till now, the way we did the t-test was that if our t-statistic was greater than the critical value, which in this case would be something like 2.01 for a 5% level of significance t-test, then we would reject the null. This would be greater than 2.01. This would be near about there. This would be greater than minus 2.01. So we reject the null. However, we don't need to do this because we are also given the p-value. So when we are given the p-value, we can do the hypothesis test simply by comparing the p-value with the level of significance. So 5% is our level of significance. Required to reject this null, or to reject the first null, is 45%. So can I reject this null? Required to reject the second null is only 0.03%. So can I reject this null? For the third null, I need 5.07%. So can I reject? The third one, I need only 0.15%. So can I reject? So the coefficients for x1 and x3, I can reject the null that the coefficient is equal to 0, or I will conclude that these two coefficients are statistically different from 0, and the intercept term as well as x2 are not statistically different from 0. An analyst would like to use the estimated regression equation from the previous example to calculate the predicted value of the current year's sales for block up. Assuming the level of industrial production is 850, he observes that the change in expected inflation is currently 5%. This is inputted in decimals, so we'll enter 0.05. The regression equation is the same as what we had derived. So compute the level of block up sales. Pretty straightforward. 8 units is the intercept term, 0.005 into the level of industrial production, that is 850, minus 22.5 into the change in expected inflation, that is 0.05. So the block up sales would be given us, or would be calculated as 11.125. Very important slide. Just like it was important in the case of linear regression, you need to memorize and understand each of these assumptions very well. So everything that we have done, all the hypothesis tests, all the predictions, all the calculations are valid if and only if all these assumptions are met. And these assumptions can be very limiting at times, and as we'll see in today's session, that these are some of the issues in the regression analysis. First, we assume that a linear relationship exists between the dependent and the independent variables. If there isn't, then you can't do linear regression. The independent variables are not random. So their value is not estimated from any regression type analysis. So their value is known or collected. There is no exact linear relationship between two or more independent variables. If I have x1, x2, x3, then none of these variables can have a very high correlation amongst each other. What is the problem that this creates? We'll study soon. The expected value of the error term is assumed to be 0. That is, Sometimes there will be positive error, sometimes there will be negative error. If this really is the best fit line, then the positive errors and the negative errors will cancel each other out, and the expected value of the error term will be 0. The variance of the error terms is assumed to be constant for all observations. The error term for one observation is not correlated with that of another observation. That is, there is no autocorrelation or no serial correlation. That also we will study soon. And finally, the error term is assumed to be normally distributed. So please spend 1 minute on this slide and try to memorize each of these points on your own. Another interesting and important test. So we skipped the F statistic during simple linear regression, and we said that we'll do it as a part of multiple regression, where anyways the F statistic has more relevance. So an F test assesses how well the set of independent variables as a whole or as a group explains the variation in the dependent variable. So this test, as we will see, is used to check if at least one of the independent variables explains a significant portion of the variation of the dependent variable. So the test is structured as, or the null hypothesis is written as, that all coefficients, let's say there are 4 independent variables, so all 4 slope coefficients are simultaneously equal to 0. The alternative hypothesis is that at least one coefficient is not equal to 0. So it wants to test that is the model as a whole useless or not. If we are able to reject this null, then what do we imply? That all of them together are not equal to 0. At least one of the coefficients is statistically significantly different from 0. The F statistic, please remember, the F distribution is again a positively skewed distribution, and the F test is a one-tailed test, and the F statistic is calculated as the mean squared regression upon the mean squared error. Please recall from the discussion of linear regression that the mean square regression is nothing but the regression sum of squares upon the number of independent variables. So the degrees of freedom of the regression is the number of independent variables upon the mean squared error, that is the sum of squared errors upon n minus k minus 1. The degrees of freedom of the error is n minus k minus 1, where k is the number of independent variables. We will see this again in multiple regression as well. However, this is the calculation of the F statistic, that is the mean squared regression upon the mean squared error, where RSS is the regression sum of squares, also called as explained variation. SSE is the sum of squared errors, also known as unexplained variation. Mean square regression is the regression sum of squares divided by the degrees of freedom of the regression, and mean squared error is the sum of squared errors divided by the degrees of freedom of the error terms. Let's do an example and understand. The degrees of freedom of the regression is equal to the number of independent variables. The degrees of freedom of the error or the denominator is equal to n minus k minus 1. N is always the size of the sample or the number of observations in one sample. K is the number of independent variables. The test is a one-tailed test. So if the calculated F statistic, which will always be positive, is greater than the critical value that we'll get from the F table, will be given in the question if it comes, then we reject the null and conclude that at least one coefficient is not 0 or is significantly different from 0. So an analyst runs a regression of periodic value script returns on 5 independent variables over 50 months. The total sum of squares is 550. That is, SST is given to be 550. The sum of squared errors, that is SSE, is given to be 190. Test the null hypothesis at the 5% significance level that all 5 of the independent variables are equal to 0. So the null hypothesis is structured as that all 5 independent variables are together equal to 0, and the alternative hypothesis would be structured as at least one is not equal to 0. The F statistic is calculated as the mean squared regression upon the mean squared error. Mean squared regression is nothing but the regression sum of squares upon k, that is 5, upon the sum of squared errors upon n minus k minus 1. The regression sum of squares can be calculated as the sum of squared total errors minus the sum of squared errors. The sum of squared total errors is 550 minus 190. That will be 360 upon the number of independent variables, that is 5, upon the sum of squared errors, that is 190, divided by the size of the sample, that is 50, minus 5 minus 1. That will come out to be 15.673 approximately. And the critical value for an F test with a 5% level of significance and the given degrees of freedom, k for the numerator and n minus k minus 1 for the denominator, comes out to be approximately 2.4. So 16.673 is greater than 2.4. Hence we can reject the null that all 5 independent variables are together equal to 0, and we imply that at least one of the independent variables is different from 0. Why we do this test and what is the application of this test, we will also study soon when we study some issues with regression. We studied coefficient of determination, that is the square of the correlation coefficient in simple linear regression, wherein it was defined as the explained variation upon the total variation. Just for the sake of repetition, the regression line does not always give us the exact value for the dependent variable, and there can be an error term. So for a given value of the independent variable, the actual value of the dependent variable is historically available. The predicted value is given by the regression equation, and the mean can be calculated from the historical values of y. The distance yi, or rather y1 minus y bar, is called total error. Of the total error, y1 hat minus y bar is explained. The distance yi minus y hat that we studied earlier at the beginning also is called the error term. So error term, generally speaking, means the unexplained error. The square of the total error is equal to the square of the explained errors, also called as regression sum of squares, plus the squares of the unexplained error, that is the sum of squared errors. SST is equal to regression sum of squares plus sum of squared. This term is known as total variation. Regression sum of squares is known as explained variation, and the sum of squared errors is known as unexplained variation. Coefficient of determination, that is the square of the correlation coefficient, is defined as the explained variation upon the total variation. Explained variation can be calculated as the total variation minus the unexplained variation. So please note that for multiple regression, the definition of the coefficient of determination remains the same. So it is calculated in the exact same way as that for the simple linear regression. Again, tells us about how good is the fit of the regression. So if it is a perfect fit, if all values lie exactly on the regression line, then all error will simply be explained error, or there will be no unexplained error. That is, the coefficient of determination will be 1. That means a perfect fit or a very good fit of the regression line with the individual data points. The lower the R square, the higher is the unexplained error, or the general fit of the regression line is not so good. So lesser the coefficient of determination, lesser the fit, the higher the coefficient of determination, the better the fit of the regression line. In multiple regression, however, there is one additional issue. The issue is that as you add more independent variables, the R square tends to increase. It's just a mathematical phenomenon. Whether or not those variables have explanatory power, or they increase or they better my regression, the R square still tends to increase. So just because R square is increasing in multiple regression, we cannot conclude that the new model is better than the old model, because the R square mathematically tends to improve as you add the number of variables. To conclude that the fit of the regression is actually improving, we compute something called as adjusted R square. If adjusted R square is increasing, then we can definitely conclude that the new model is a better fit than the earlier model. So adjusted R square is calculated as 1 minus n minus 1 upon n minus k minus 1 into 1 minus the unadjusted R square, or the regular coefficient of determination. If the adjusted R square is increasing, then the new model is a better fit. Please take a moment to remember this formula. We'll apply it in the next question. An analyst runs a regression of periodic value script returns on 10 independent variables over 50 months. The total sum of squares is 550 and the sum of squared errors is 190. Calculate R square and adjusted R square. R square is calculated as the explained variation upon the total variation, that is the regression sum of squares upon the sum of squared total errors. The regression sum of squares can be calculated as the sum of squared total errors minus the sum of squared errors upon the sum of squared total errors. This is given to be 550 minus 190 divided by 550. This will come out to be the R square for the regression. The adjusted R square is calculated as 1 minus n minus 1 upon n minus k minus 1 into 1 minus the original R square. Again, this will be calculated as 1 minus 50 minus 1 upon 50 minus 10 minus 1 into 1 minus the R square, that comes out to be 0.654. The adjusted R square would be this minus 0.654, that is 0.566. Now the analyst adds 5 more independent variables to the regression, and he finds out that the R square has increased to 68% from the earlier 65.45%. Identify which model should the analyst use, or which is the better model. So again, just the R square going up is not enough evidence. We need to check for the adjusted R square and see how that moves to conclude which model is a better fit. So once again, let's calculate the adjusted R square. It will be 1 minus n minus 1. The sample size remains the same. However, the number of independent variables has now become 15 minus 1 into 1 minus the R square, that is 0.68. So the adjusted R square comes out to be 0.538. The adjusted R square earlier was 0.566. So the adjusted R square actually has gone down. Hence, the new model actually reduces the explanatory power of the regression. So adding these 5 more independent variables does not add much value. The earlier model had better predicting power. We should use the earlier model. In simple linear regression, we studied the example of a partial ANOVA table. We will now use a complete ANOVA table and try to make inferences about the regression analysis. So in an attempt to estimate a regression equation that can be used to forecast Blockup's future sales, 20 years of Blockup's annual sales were regressed against 2 independent variables, as we saw. IP is the level of industrial production and delta I is the changes in expected inflation. The output from a common statistical software package is contained in the following table. Based on the output in the table, the regression equation can be stated as the Blockup sales are 8 units plus 0.005 times the level of industrial production minus 22.5 times the change in inflation. Fill in the missing data and interpret the results of the regression at a 5% level of significance with respect to the significance of the individual independent variables and the utility of the model as a whole. So there's 3 questions. First is to fill the missing data. Second is to judge the significance of individual variables. And third, to judge the utility of the model as a whole. So we'll first start by analyzing the table and filling in the missing data. We're given the coefficients, we're given the standard errors. The first question mark is next to the t statistic. So the t statistic can be calculated as the coefficient upon the standard errors. 0.005 upon 0.004, that is 1.25 will be the t statistic for the coefficient on the level of industrial production. Similarly, the coefficient here is minus 22.5 and the standard error is just 3.675. So the t statistic will be calculated as minus 22.5 upon 3.765, that is minus 5.9761. The degrees of freedom of the regression is equal to the number of independent variables, that is k, that in this case is equal to 2. The degrees of freedom of the error term is equal to n minus k minus 1, that is equal to 20 minus 2 minus 1, that is 17 units. The mean squared regression is the sum of squared regression divided by the degrees of freedom of the regression. So it will be 235 divided by 2, that is 117.5. The mean squared error will be the sum of squared errors divided by the degrees of freedom of the error. That will be 115.17 divided by 17, that is equal to 6.77. The F statistic is nothing but the mean squared regression upon the mean squared error, that is 117.5 upon 6.77, that is 17.34. The total degrees of freedom will be the sum of the two, that is 19, and the total error or sum of squared total error would be the sum of the two, that is 235 plus 115, that is 350.17. Okay. The R square can be calculated as the sum of squared regression upon sum of squared total, that is 235 divided by 350.17, that is equal to 0.67 approximately. Similarly, the adjusted R square can be calculated as 1 minus n minus 1, that is 20 minus 1, upon n minus k minus 1, that is 20 minus 2 minus 1, into 1 minus R square, that is 1 minus 0.67, comes out to be 0.63 approximately. So we filled in the missing values in the ANOVA table as the first part of the question asked. The second part wanted us to make a judgment on the significance of the individual coefficients. So the p-value is given and the level of significance is given to be 5%. So for the intercept, the minimum level of significance required to reject this null is 15%. Our level of significance is 5%. So we cannot reject the null that the intercept is equal to 0. So the intercept term is not statistically significant. Similarly, for the level of industrial production, we need a 32% level of significance to reject the null. So we cannot reject the null, and we cannot conclude that this is also statistically different from 0. The changes in expected inflation have a very low p-value, so we can reject this null and conclude that this is different from, or statistically different from 0 at a 5% level of significance. The last part of the question asked us to judge the utility of the model as a whole. The utility of the model as a whole can be judged by two parameters. First is the R square, or the coefficient of determination, that tells us how good is the fit of the regression. So about 67% of the variation in the dependent variable is explained by the independent variables. We can also look at the F test that tries to tell us that as a whole is the model useless, that is, are all coefficients simultaneously equal to 0? So again, the p-value is very low. So we can reject this null and conclude that at least one of the coefficients is statistically different from 0. Please verify your answer. We next move on to a very important concept of dummy variables. So please remember, dummy variables are simply independent variables that can take on a value of either 0 or 1. Probably that's why they call dummy, because they can only take two values, either 0 or 1. The formulation of the regression equation using dummy variables remains the same as we studied earlier. So if we are trying to project the quarterly EPS and we use three independent variables, Q1, Q2, and Q3. Q1 is 1 if we are in quarter 1. At all other times, Q1 is 0. Q2 is 1 when we are in quarter 2. At all other times, Q2 is 0. Similarly, Q3 is equal to 1 if we are in quarter 3. At all other times, it is equal to 0. B0 is the intercept coefficient, that is the expected EPS when all Q1, Q2, Q3 are 0. That means we are in the fourth quarter. So let's see what would be the possible data for estimating a regression like this. So if we see the last 40 quarters of EPS, then the EPS values would be something like this. So on and so forth. So let's assume that this was the first quarter of year 1, the second quarter, third quarter, fourth quarter. For the next year, this was again the first quarter, second quarter, third quarter, so on and so forth. So I had 40 different values. There would be 10 first quarters, 10 second quarters, 10 third quarters, and 10 fourth quarters. So if I'm in the first quarter, this is the value of the EPS, the historical value. The value of Q1 would be 1, Q2 would be 0, and Q3 would also be 0. Similarly, in the second quarter, Q1 would be 0, Q2 would be 1, Q3 would be 0. In the third quarter, Q3 would be 1. In the fourth quarter, all three would be 0. Similarly, I can plot the independent variables as well as the dependent variables for all 40 time periods. Once I have plotted the historical data, the problem now is of any other multiple regression. That is, I have 40 historical values. I know the dependent variable. I know the independent variables. And I need to find out the coefficients B1, B2, B3, and B0 using the ordinary least squares method. So this would be an example of a regression using dummy variables, wherein the independent variables can only take a value of 0 and. Please note, however, what does B0 now indicate? B0 indicates the average value of the EPS when all Q1, Q2, Q3 are 0. That is the average value of the fourth quarter's EPS. What does B1 indicate? Please note, B0 is always there. So B1 indicates that when Q1 is equal to 1, that is, we are in the first quarter. How much does the first quarter EPS differ from the fourth quarter EPS? Because the fourth quarter is always there, B0 is always there. B2 indicates that when Q2 is 1, or we are in the second quarter, how much on an average does the second quarter EPS differ from the fourth quarter EPS? That is the application and interpretation of the coefficients using dummy variables. For example, if the regression equation is estimated to be that EPS is 1.5 plus 0.6 times Q1 minus 0.15 times Q2 plus 0.12 times Q3, then the average fourth quarter EPS is 1.5, that is B0. The average first quarter EPS would be how much? 1.5 plus 0.6. So on an average, the first quarter is 0.6 units higher than the fourth quarter. The average second quarter EPS would be 1.35, that is 0.5 units lower. The average third quarter EPS would be 0.62, that is 0.12 units higher than the fourth quarter. So remember, the estimated regression coefficient for the dummy variables indicates the difference in the dependent variable for the category represented by the dummy variable and the average value of the dependent variable for all classes except the dummy variable class. So this is the fourth class. So the average value of all classes except the dummy variable class is 1.5, and this coefficient represents the difference from this value. To distinguish between n classes, for example 4 quarters in this case, please remember we have to use n minus 1 dummy variables. So we cannot use Q4 also as an independent variable. That would create problems in the regression. The problem is the assumption of no exact linear relationship between the dependent variables would get violated, because 4 quarters, you would agree, would to some extent be related to one another. The sales in one quarter would be related to the sales in another quarter, and the assumption of no multi-collinearity that we will study is that independent variables cannot be strongly correlated with one another. That is why if there are n classes, you must use only n minus 1 independent variables. Just like we did the hypothesis test for other regression coefficients, we can do a hypothesis test for the dummy variable coefficient. So a test or a null hypothesis that B1 equal to 0 essentially argues or tests that whether the fourth quarter EPS is the same as the first quarter EPS, because if B1 is equal to 0, that means the fourth quarter EPS would be the same as the first quarter EPS. There will be no difference. Similarly, a test for B2 equal to 0 would test whether the fourth quarter EPS is the same as the second quarter EPS. And for B3 equal to 0, we are testing that whether the fourth quarter EPS is the same as the third quarter EPS. The hypothesis test remains the same. The t statistic is the coefficient divided by its standard error, and the t value or the critical t value is calculated from the t table with n minus k minus 1 degrees of freedom. If there are 50 data points with 5 variables, then it will be 50 minus 5 minus 1. The standard error of the coefficient B1 is equal to 0.2 from the EPS regression model. Test whether the first quarter EPS is equal to the fourth quarter EPS at the 5% significance level. The standard error is 0.2. The value of B1 we estimated was 0.6. The t statistic can be calculated as 0.6 upon 0.2, that is equal to 3 units. The critical value is somewhere in the range of 2.01. It will be given in the question. So we can conclude that as the calculated statistic is greater than the critical value, we can reject the null hypothesis that B1 is equal to 0, and we imply the alternative, that is B1 is different from 0, or the first quarter EPS is statistically different from the fourth quarter EPS.